Good morning, dear participants, and welcome back to our final and concluding session of FDP. Let me introduce to our resource person, Dr. Sanjay Sengupta. He is a professor in the Department of Civil Engineering at Dr. BCREC Engineering College, Durgapur, where he is serving since January 2024, 2014. He holds a PhD in Civil Engineering from NIT Durgapur, MTech from Structural Dynamics IIT Roorkee, and BE in Civil Engineering from NIT Silchar. With total professional experience of 15 years in teaching, 6 years in research, and 10 years in industry, he also previously worked with Tata Consultancy Services Limited in multiple roles where he rose to the rank of associate consultant. His key research interests include earthquake engineering, structural dynamics, structural health monitoring, and soil mechanics and foundation engineering. Dr. Sengupta has published in reputed journals and conferences, contributing to book and book chapters, and effectively participates in different academic and institutional activities. He has published 12 journal papers from different SCI and Scopus Index journals, one book and 11 book chapters, with 18 conference papers. With total 25 years of experience in industry, research, and teaching, Dr. Sengupta continuously strives for providing quality education through his different administrative roles as head of the Internal Quality Assurance for the Institute and state level mentor for NAC accreditation that is assigned by the government of West Bengal. On behalf of Dr. BCREC Engineering College, Civil Engineering Department, I welcome Professor Sengupta. The session is over to you.
Thank you. Thank you, Professor Biswas. It's a great pleasure to be present in this faculty development program as a speaker. On this occasion, the faculty members who are joining this FDP program, I like to thank you all for joining this faculty development program and listening to my lecture. As well as in front of me, some students are also present who are also listening. So not doing much delay, I'll directly go to my presentation. And today's topic on this, I'll just share my window so that everyone can see. Online participants, can you see my shared screen? Okay, thank you. So today I'm going to speak on the faculty development program on smart city planning through civil engineering innovations. And today's session will be on structural health monitoring for smart structures. So before I go into this presentation, let me just focus something on this smart structure. So what kind of structures will you call it as a smart structure? That is very important. And when you talk about smart structures, throughout this FDP, different sessions, you have learned about different smartness in the structures or relevant infrastructures need to be put, where you have observed that any smartness comes in a structure using some kind of mechanism where some data to be captured from the structure such that that data can be used for some kind of validation or some kind of checking for the structure. So if I go to the smart structure introduction, then you see smart structures are basically those kind of structures which integrates technology, infrastructure, and data. So it's not only about technology. Like many cases, you in today's world, you are talking about artificial intelligence, machine learning, and all these things. But those are kind of tool you can use where you require data. And from where you will get the data? Data will come from technology. So basically, these technological devices needs to be integrated in the infrastructure, and from that data needs to be collected. And that technology primarily is basically nowadays you can hear about lot of hearing. You can see about Internet of Things, that is IoT technologies and sensor-based technology. So in today's talk, I will mostly focus on real-time sensor-based technologies. But before I get into that, I'll just go through the introduction part. So you see the infrastructure, actually, why do you require smart structures? The smart structures are required because you see the infrastructural safety is the primary important thing. And for infrastructural safety, it is required. Why is it required? It is required because you require public safety, you require economic sustainability, and you require the disaster resilience for kind of the structures you will be catering to. Now, if you go for the different kinds of structures, then you see there is a need for real-time structural monitoring. Because you see, whenever there is a problem in a structure, in the real time, you should be able to capture the data. And from that data, you should be able to comment on the structural deficiencies. That is very important. It is just like our health, right? So like our health gives some indications before we fall sick. So structure also gives some indication about its health before it falls completely sick. So that is very much important. So in the real time, you need to require to collect the data for the structure. Now you see, this is what you can see. I think a complete city infrastructure where I think partly the slide is getting cut over here. I don't know why. So if you see, this is a typically smart city infrastructure, and here you can see there are different types of integrations are required, and these different types of integration will basically consist of, first thing you require for any smart kind of structure, you require Wi-Fi wireless signal icon, or Wi-Fi wireless signal connectivities, right? So the connectivity, IoT networks, real-time transmission, these are the most important thing of any smart infrastructural facilities you are catering in a smart city. Then you see, you require smart energy innovation kind of thing. So energy, whatever energy you are generating, that needs to be smart enough. That means the energy requirement of a particular city or a particular structure or infrastructure requires to be determined, and it should be smartly utilized. So that is another one most important thing in case of smart structure. Then you see, you have security, cyber security. So the more the data you are having, you are making open it to the internet, you are having access to the data, like lots of threats comes, and the cyber security comes into picture in that case. So lots of things you will be required to maintain using your secure system, and there should be a tremendous importance given for the surveillance system. Next, you see, you require structural integrity. Structural integrity means that is very important. This is what is the point of discussion today. I'll be highlighting on that is, you require to monitor and you do a predictive maintenance for different types of infrastructure. The infrastructure may be of any kind. It may be bridge, it may be tunnel, it may be building, any kind of things. Next, you can see that one of the very, very important thing in today's perspective, you see the temperature. Cities are burning because of the heat. So you need to control the temperature and heat. And you know that the more the evolvement of this AI and these different kinds of data processing things are happening, the more and more the requirement of data centers are coming into picture, and those are generating huge amount of heat, and that requires lot of cooling, and those cooling, that amount of cooling requires a lot of water. So in case of a smart structure management, you require to control on your environment, where there should be environmental sensing, weather sensing, and you must focus on climatic control thing. Next, you see the water drop icon. If you see the water drop, and this is another one thing, I think two or three speakers in this FDP have focused on this water management thing. And you know, like in case of any smart infrastructure will go in vain. The way the more you talk about AI, cyber security, these, that, whatever you talk about, if you do not have water and if you do not have power, nothing can be worked out. So you need to focus on the water management and quality monitoring of the water. Next, you see that you require to focus on different kind of network system, because you see all the things I have mentioned that needs to be networked, right? So all the things like your health of structure, your cyber security thing, your temperature thing, your connectivity thing, that needs, all this needs to be integrated together. Then only you will be able to capture the data. And for that, you require lots of data connection points, and that data connection points needs to be processed, and it should be collected through network data, network system. And then you can have your different kinds of analytics, and from that analytics you can comment on the smart structure, how smart it is, whether you require any improvement, whether you require any kind of further development to it. And another point I think you should also concentrate on, that is the traffic flow. And the traffic flow is the another one most important thing you should be always considering in case of any kind of smart cities, or in case of the smart infrastructure you are developing, while for transportation and for any kind of traffic flow movement. Now you see, for all these things, whenever you are trying to do the collection of data, then you require what? You require actually some distributed network of sensors, because unless you have sensing technologies coming into picture, you cannot collect the data. So you require to have sensing technologies and some kind of devices which should be able to do the real-time monitoring of all these cases, as I have mentioned. Now you see the importance of structural health monitoring. The first thing you see, the importance is the structural health monitoring. Actually, shortly it is called SHM, and that SHM, what does it do? It basically does the early damage detection, because you see in case of our health also it happens, like if we are falling sick, then we go to doctor prescribes something, and then we take medicine, and then it gets corrected, right? So as soon as we can identify that our health is getting deteriorated, then only I go to the doctor, right? Right? Then we go to the doctor. So in case of a structure cannot speak, right? So this speaking by the structure will be done using different kind of technologies like Internet of Things, the IoT technologies, or the sensor technologies. Okay. So first thing you should understand in case of any structural health monitoring is detection of the damage. So if there is a damage happening in any kind of infrastructure or structure, then you need to determine it very early. Next is this structural health monitoring, if you can do, what will happen? It will reduce the maintenance cost of your structure, because as soon as you identify your defect, then you have the options for correction. So if you do the correction, if you medicate the structure with some medicine, then obviously it will live longer. So basically that will help you in reducing the maintenance cost, as well as it will give you the extended service life of the structure. It is just like your physical health, nothing else. Next, you see, as you all know, where you can apply the structural health monitoring technique. You can apply this health monitoring technique to anything, any infrastructure. So you can go, you can do it for bridges, you can do it for buildings, you can do it for tunnels, you can do it for dams, you can do it for any kind of infrastructure. So that's what structural health monitoring application is. A it can be widely used. You can use it for transportational infrastructure, right? Like roads, bridges, rail, traffic systems. You can do it for energy infrastructures like power grids, sustainable renewable energies, substations and renewable energy stations. Then water and infrastructure management, very, very important. Pipeline systems. In one of the lectures of FDP, we are also listening that the leakage of water is damaging the is being to be controlled, and for that you require the structural health monitoring of the pipelines, right? Pipelines health monitoring, treatment lines health monitoring, drainage system health monitoring, these are very important. Then you see all these things we are talking about, this AI, this machine learning, this approach, internet approach, all will fail if the telecommunication network fails, right? So it's a very important thing that the telecommunication network should be stable, things. And for that, you require to maintain the health through structural health monitoring techniques for fiber networks, 5G networks, data centers. And then obviously you are having building and urban infrastructure. This is the most common thing comes into our mind. That is residential complexes, commercial buildings, public buildings, and the last, the public safety infrastructure. You see, the surveillance system, energy response system, these are also very important, and that also needs to be monitored through structural health monitoring. And above all, if our environment is not sustainable, then everything goes in vain. So we need to protect our environment also through this health monitoring purpose. And you need to require the quality, you need to maintain some health monitoring technique for your air quality monitoring and the climate monitoring. So I think you have now have some idea about where we can apply the health monitoring techniques. So in civil engineering field, if you think about, then any infrastructure you talk about, there is an application of structural health monitoring. Now you see the traditional structural health monitoring technique and the real-time health monitoring technique, they are having some differences. So earlier days and even in today's world also, there are different traditional SHM techniques has been used. And the most common technique you can see, this is what is the most traditional SHM technique, that is visual inspection. What you can see, a person, an engineer is going and visually inspecting the pipeline, right? So he is trying to find out where is the leakage is there. He's trying to write a report. Then he will be supplying the report to someone, and then another engineer will come and will rectify the defect, right? So this is what is the kind of visual inspection. And this is common kind of structural health monitoring technique which existed long back. It's not, structural monitoring is a very new term coming into in this new era. It's not that structural monitoring is a very new term. It was happening. Now next is, you see, the non-destructive kind of testing, because you do not want to destroy anything and still you want to monitor the health. So in such a case, what you can do, you can use the ultrasonic testing facility, and you can have the ultrasonic testing machines where you can do the quality checks. So you just pass the ultrasonic waves through the material which you want to check, and if you want to check it, then the velocity of the ultrasonic pulses, travel velocity, if you can monitor, from that you should be able to comment on the quality area. Okay, so it can be very easily ultrasonic test meter. Then you see there's a very common type of technique which is traditionally used for structural health monitoring, that is vibration based monitoring technique. And in this vibration based monitoring technique, like you have some vibration sensors you can use. You can use different kinds of strain gauges. So what you can do, you can just vibrate the thing, and after the vibration, if you can get the sensing thing from the accelerometer or some vibration sensor, and you can collect the data from that, you should be able to comment on the health of the structure. Now, what are the limitations of this structural health monitoring technique? So you see the primary limitation of this traditional structural health monitoring technique is they are periodic and non-continuous. See, you cannot continuously monitor the health of the structure, right? So it is periodic. Sometimes you go check it, and then you comment on it, and then you rectify it. So it is periodic and non-continuous. Next is it is labor intensive, because like whenever there is a manual thing manual thing involved, then you need to go and check it. So there is a lot of labor required for this, and there is a chance of mistake to be done if the labor or the engineer who is inspecting, he is overburdened with the inspection responsibility. Okay, so that is where the point of concern for traditional health monitoring technique, where you may miss the early stage of damage. As soon as the damage starts, you may miss it with your traditional health monitoring technique. After the damage, you may find it out, the damage has happened and you can rectify. But if you want to find out the onset of the damage has just started to happen in any structure, then using traditional structural health monitoring technique, you may miss it. Now, with this limitations of structural health monitoring technique with the traditional health monitoring techniques, there is a new concept came into civil engineering, that is called acoustic emission technique. And this acoustic emission technique, it's a kind of a technique where you can do a passive non-destructive testing. Passive means you need not to worry about, and you need not to go to the structure for inspection, or you need not to wait for the structure that damage is visible. If you are having some internal damage of the structure also, you can monitor that structure through the real-time health monitoring concept. It's a passive non-destructive testing method. And what does it do? I'll clear it with a simple diagram to you. Basically, in the next slide, next point, you will see actually what it does, it detects stress-induced energy waves in real time. Basically, as soon as a defect happens in a structure, as soon as crack happens in a structure, it will propagate like a sound wave. Because you see, any crack will come up with some feeble sound also, right? Any crack will come with some feeble sound also. And when there is a sound, that sound wave will be propagating through the structure. And by any means, if we can catch hold of that movement of that wave, then we should be able to find out whether the crack has happened, whether the crack is enlarging, whether the whether where the crack has happened, and how the crack has happened. All these things we should be able to identify. So what is the diagram you can see? You can see any structure when it is under some load that will be uh, able to take up the load. But if any crack generates, you can see here any crack generates. If you see there is a crack getting generated over here, and whenever there is a crack getting generated, what is happening? You can see that basic principle, if you observe, then what is happening? The damage. So this is what is the damage. The crack is getting generated and the damage, and this damage is doing what? This is doing the release of elastic energy. This is as soon as the damage happens, it will give rise to some elastic energy release, right? Once this elastic energy release happens, so I just try to show it with this arrow. So there is a damage and then release of elastic energy, and after that you see the energy travels as stress wave. So you can see this is the wave it is propagating. So the energy will travel through the medium as wave, right? So as soon as you will see this energy will travel through the wave medium as wave, and then you can see these sensors, and these are called acoustic emission sensors. And these sensors can be mounted on the structure, and those sensors will capture the wave signal, right? So as you get the wave signal captured, you should be able to comment on the structure. So you see, the signals can be analyzed for damage characteristics. So once you get the signal, you can analyze that signal for damage characteristics. In the second part of my presentation, while I'll be showing you some demonstration, there you'll be able to see how these signals can be processed for damage identification, damage quantification, such kind of thing. So I'll show you with the demonstration part. Now you see, this is what is actually the workflow diagram for any kind of acoustic emission technique. This is very simple. You see, there is a crack is happening over here, and once the crack is happening, I think I should show it with mouse. So once the crack is happening, you can see once the crack is happening, there is a source, wave is propagating, and it is being collected through sensor, and this sensor will be transmitting through some cables to the preamplifier, because you see, whenever the signal is generated, you need to pre-amplify, because that may be a very feeble signal and that needs to be amplified. So it will pass through a pre-amplifier. After that, it will get into a data acquisition system. This is very important. This is DAQ, data acquisition system. And in this data acquisition system, the processing of the signal will happen, and then this will be passed to a monitor where you can see the recording and the display of the signal. Okay, so this is actually acoustic emission data flow diagram. And the component of acoustic emission monitoring system, you can see they are consisting of these only parts. That is, one sensor you require, then you require preamplifier, you require data acquisition system, you require signal processing software, and obviously if you want to become smarter, then you require what? You require communication network, because you'll have to communicate, right? So you need to communicate it to the outside world, or you need to communicate it to your data center where the processing will happen. So there is a communication network required. Next, you see the emission occurs. What is the cause? What are the causes of emission? So emission, this emission of due to this AE waves, of the emission of these AE waves actually happens because of what? Because of crack initiation. This is very important, this crack initiation. So you see, whenever there is an initiation of the crack, which you could not identify using traditional health monitoring techniques, that can be very easily identified using acoustic emission technique in the real time. And obviously, after the initiation part, you can also identify the crack propagation. So if there is more development of the crack, the different kinds of signals you will be expecting. I have a slide for that. You'll be able to understand how it will be happening. And then obviously, if there is a crack, if there is a different kinds of enlargement of the crack, so what will happen? There will be deformation in the material, and obviously from that indication you should be able to rectify the problems whatever is happening in your structure. So next is, you see, this is a basically a setup of typical setup, experimental setup of acoustic emission thing. And you can see this is the setup at structural health monitoring lab of NIT Durgapur, National Institute of Technology Durgapur. You can see this is what is a preamplifier. This is what is preamplifier, and then there is a sensor. You can see the sensor is attached to the preamplifier, and this preamplifier is attached through a cable, and these cables are called BNC cable, and these cables are attached to the data acquisition system, and this data acquisition system is attached to a monitor. Okay, so that the flow diagram I have shown you, this is the practical example of the flow diagram. That is how the setup looks like in laboratory. Okay, so this is the enlarged version of your data acquisition system. This is the data acquisition system of Physical Acoustic Corporation. One of the biggest company who are developing and giving the solutions for the acoustic emission things. And next you can see this is in a little enlarged version of this data acquisition system, where you can see these are the cables. You can see these cables. These are the cables which are attached to the preamplifiers, and the preamplifier will capture the signal, amplify it, and pass it to the data acquisition system. Now you see the typical setup in a laboratory setup. There is a check for a railway sleeper, railway uh, railway thing is being done, and you see here these are the sensors. You can see these are the sensors. These are acoustic emission sensors. And you see these sensors are attached with small cables to these preamplifiers. So you can attach multiple sensors. You can attach multiple sensors. And then from the sensors, you can see these cables. And these cables are finally attached to this data acquisition system. So this is the typical setup you require to do for any kind of acoustic emission setup. This is another one example for a laboratory setup for aluminum plate, which has been done. Now next, if I go to the concept of acoustic emission, you need to understand, because you see the data acquisition part, pre-amplifying part you have understood. Now sensor. So sensors, acoustic emission sensors, how they are different from accelerometer or vibration sensor or ultrasonic pulse sensor. How are they different? So the difference of the acoustic emission sensor you can very easily find out if I explain you, when I explain you the types of AE sensors we generally use. That there are different types of AE sensors used, but primarily you see the acoustic emission sensors are basically piezoelectric sensors. You know the piezoelectric material you have studied in your 12th standard also, and later on also in different parts we have studied piezoelectric materials. In the piezoelectric material, what happens? It's a such a sensitive material where if there is a very small kind of deformation comes in a piezo material, it generates electricity, electric pulse. Okay, and that electric pulse can be transferred, and that can be pre-amplified, captured, and that can be considered as the acoustic emission signal. So basically if you see the acoustic emission sensor, particularly they are basically piezoelectric sensors. And along in this piezoelectric sensors, you can have primary two kinds of acoustic emission sensor. One is wideband sensor, and the another one is resonance sensor. So you can see the piezoelectric sensor, as I have told you, that it uses piezoelectric materials that generate electrical signal when stressed by AE waves. They are most common AE sensor. They are most common AE type of sensor to high sensitivity, robustness, and suitability for many materials and structure. Now, next is your wideband sensor. So, what is wideband? So, wideband sensor means acoustic emission signals actually generates very high frequencies. Like, right, the frequency generated in the acoustic emission signal goes into kilohertz. Okay, so 1000 kilohertz, 100 kilohertz, 150 kilohertz, 200 kilohertz, 250 kilohertz. That kind of range of frequency you will be getting from acoustic emission signals. Okay, which are very difficult from your structural frequencies. If you take the frequency of your structure, that may be ranging into hertz, whereas the crack which will be generating the signal of acoustic emission and which will be captured through acoustic emission sensor, they will be having very high kind of frequency range. And if you want to collect uh, um, uh, huge amount of frequency or different ranges of frequency and a broader ranges of frequency, then you need to use wideband sensors. On the other hand, if you know in a typical structure, this kind of cracks are going to be generated, and within this frequency range, these cracks will be coming. So in such kind of cases, you can use resonance sensor. So resonance sensors are also piezoelectric sensors itself, and they are the sensors which are tuned to be most sensitive at specific narrow frequency range. Okay, and they provide higher sensitivity than your wideband sensor. So if you see the typical kind of acoustic emission sensors which we are seeing in the previous diagram in a very smaller thing, you can see the enlarged scale of it. So this is the kind of a acoustic emission sensor. These are being sold by Physical Acoustic Corporation of America. And you see this acoustic emission sensor. Can you observe that on the top it is written R alpha, R6 alpha. Okay. So this typical R6 alpha, this kind of sensor, they are actually resonant sensor. So, and their frequency range is limited between 35 to 100 kilohertz. So if you know that your cracks which will be generating a signal of range between 50 to 100 kilohertz, then you can use this kind of sensors. Okay. So you see, if you know which kind of signal will be generated by which kind of crack, and if you know your structure is going to be vulnerable because of the load and which kind of crack may be coming in your structure, that means in case of a known kind of thing, you can use this kind of resonance sensors. However, if you do not know which kind of crack is going to come and you do not know the range of frequency, then you should go for wideband sensor. So now this is a typical kind of resonant AE sensor. Then another resonant AE sensor, you see, if you want to go for a little higher range of thing, then you can use, see there, there is a sensor it is a different sensor. This is R30 alpha. So R30 alpha is another one kind of sensor which you can collect a wide range, much wider range, that is 150 to 400 kilowatt signal. If you want to, frequency, if you want to capture, then you can use this kind of sensor. On the other hand, if you are not sure about which kind of frequency is going to come, you can go for wideband sensor. And you can see this wideband sensor here. You can see that WD sensor. This WD sensor you can use for a range of frequency from 100 to 900 kilohertz. You can see the range 100 to 900 kilohertz. So in the initial case, you are observing 35 to 100, then 150 to 400. But wideband sensor, if you use, you can capture signal frequencies, any kind of signal frequencies, which will be generated by acoustic emission in a range of 100 to 900 kilohertz. Now, obviously, you can now understand that which kind of AE sensor you will be selecting. That will depend on your material type, then frequency range, and the environmental conditions. So next, you see, you need to understand now, if the sensor is generating a signal, what is the signal will give you? And that is where you require to know the signal parameters for a signal. And like a signal has got different kind of parameters. I will explain you with the diagram. You see, this is the typical kind of acoustic emission signal you are going to get. And in this acoustic emission signal, you see that at one side you are plotting what? Time. On the x-axis, you are plotting time, and on the y-axis, the amplitude is plotted. And amplitude is in millivolt, right? Because you see the piezo is giving what? Piezo material is changing the mechanical thing to the electrical thing. So the electrical part in amplitude, electrical signal amplitude you are getting, it is in millivolt. So in this case, if you see, typical A signal will look like this. And you see, there is a term called threshold given over here, threshold. So this threshold needs to be identified from where the A signal will start. Okay. So that comes from your experience, that comes from the different literature you are having. So different kinds of materials will have different kinds of acoustic emission threshold. Okay. And that threshold, once you define, and beyond this threshold, when the signal starts occurring, you can see this is the range where the threshold has been crossed, and this threshold region will be considered as the effective, or this is what is the duration of the acoustic emission signal. And out of this acoustic emission signal generation, you will get a typical peak somewhere, and that peak will be called as the rise time of the signal. And you can see there are multiple peaks and throws, and one peak and throw in this case, if you count it, that will give you the hit count. The number of counts you are going to get, that will be given by a hit count. So basically what you are seeing here in this diagram, in this typical A signal, it is that time plotted against what? The amplitude. That's all, right? And there is a threshold. So in the demonstration part, I'll show you how to take a threshold and how to use this typical kind of signal generated in a concrete slab, let's say, for finding out where the defect is happening. And now, these are the parameters which will help you for identifying the damage severity, the damage location, and the damage type. So these are the three things we will be focusing on in any case of structural health monitoring of smart structure also. Now I have spoken about the crack and crack growth. And in all the cases, if you remember, I was telling that I'll show you a slide that how a signal will be changing with the case of crack growth. So you see, this is a typical kind of slide I have kept. Here you see the stage 1. It is showing you the micro crack initiation. Just a crack is getting generated. And you will be able to track it. You can see the nature of the signal over here. The first, you see the low amplitude signal you will get. Okay. Then you see if the growing of the crack is happening. So if the growth of the crack is happening, more energy will be generated. And as soon as the more energy generates, you will get moderate kind of AE hits. And you see the signal changes, right? So the preamplifier, through the preamplifier, whatever signal you will be collecting, your amplitudes will be getting changed. And you see more rapid growth of crack in the stage 3, unstable crack growth is happening. You see what you are getting? You are getting high amplitude signal. And at the end, you will get the fracture, right? So our aim in any case of health monitoring technique, structural health monitoring, what we are looking for, it is the real time. So real time, when it will happen, you should be able to restrict at the stage 1 itself. So as soon as the micro crack generates, this is the strength of real time health monitoring using acoustic emissions technique. So once a crack just initiated, micro crack initiates, if you can get the signal using the acoustic emission, you should be able to get the location of the crack, and you should be able to rectify that crack. So that is what is the aim of acoustic emission technique. Now you see there is a demonstrative just video. This is how things happen. You see, I have taken it from one of the acoustic emission company. They are selling this acoustic emission thing, and you see how it is happening. So can you see there is a steel plate, okay? And in this steel plate, you see the crack is happening, and you can see the sensors are attached. The sensors are attached. This is a sensor. This is a sensor. This is a sensor. So these sensors are attached to a system, and this system is attached to a monitor, right? And in this monitor, as soon as the crack is just increasing, you can see more number of dots are coming. More number of dots are coming, right? Red dots. What does it mean? That means the AE signal energy is getting generated more, right? AE hits are coming more. So that is what is the crack initiation to crack growth stage. Okay. So now you see, if you can observe this diagram, what you are observing here, in this diagram you can see that preamplifier thing has vanished. There is no data acquisition system, there is no preamplifier. Correct or not? Sensor, then it is going to something, and then it is going to the terminal. But if you remember, the first diagram I have shown you, there you had sensor, then there was a cable through which it is going to preamplifier, then preamplifier to data acquisition system, then data acquisition system to monitor, right? But here you see, there is no such kind of preamplifier and all. And this is what is today's requirement. In today's smart health monitoring system, you require a kind of remote acoustic emission management system where everything will be embedded inside a thing. Okay, so the in this only your preamplifier is embedded. Okay, your data acquisition system is itself this one, and this can be also connected. Here you see this is connected through a cable, but this may not be connected through a cable. You can have wireless system also. So you can have Wi-Fi, and the Wi-Fi will transfer the signal to the to your computer, to your cloud, to your data storage device. Okay. So that architecture in the next slide will try to see such kind of architecture we'll try to see in this. This is what is actually the smart architecture of acoustic emission. Okay, or any kind of sensor technology. If you see the smart architecture, so you can see at the lowest layer you are having the applications, right? You are having the applications. So different kinds of applications. See here you are having bridges. Here you are having pressure vessel. Okay, then water treatment thing. So any kind of structure needs to be monitored for health. And you see here you can see there is a term written RAEM1. So what is this? RAEM1. This is a device. It's a single type of AI device which integrates everything, which is collaborate, which keeps everything like AI sensor, like resonant or wideband sensor. Then it is basically an integrated acoustic emission monitoring system. Okay, so once you have this system in place, so your signal will be captured through this RME1, and then you can find out that next part is your communication layer. And you see in this communication layer, there are different protocols through which the data may be communicated from the RME1 to your cloud system. So the next part is the data data terminals. You can see the data terminals here. You can see different kinds of storage devices are given. So you can have database. So you can store the data. You can have web. You can have application. Anything you can have, but you require to connect this RME through some Wi-Fi kind of network. Okay, and when you require to connect this through Wi-Fi kind of network, let's say you are connecting it to a bridge will be anywhere, right? Anywhere. So if you want to do it, you if you want to work a Wi-Fi system, any Wi-Fi system or any kind of wireless kind of system also will require some power, right? Also, it will require some power. So if you think about in a remote place on a river, there is a bridge. So how do you supply power to that? So for that, like there is a thing called LoRa. That is LoRaWAN system. So LoRa is nothing but low power, low range wireless communication technology. This is a wireless communication technology that is actually part of electronics. That is low power, low range. Okay. Sorry, low power, long range, not low range, low power, long range. So with a very minimal energy consumption, you should be able to transmit whatever the signals you are capturing through this RAEM1. Through that, whatever you are capturing with this LoRaWAN, you should be able to transmit it to the cloud system. Once you get it in the cloud, once you get it in the server, you can very easily extract to your local devices. You can extract to your local computer. You can process it. You can comment on it. Okay. So this is what is the architecture of a smart structure system. Have you understood? So this is what is actually real-time health monitoring of structure using acoustic emission technique. Okay. So what do you require? You require IoT enabled AE sensors. You require wireless data transmission. You require cloud-based data storage. You require AI-driven analytics. So all these things are required to see the AI-driven analytics will come into picture, but all the other things needs to be controlled. So it's the integral part of civil engineering, electronics engineering, computer science engineering. So it's basically interdisciplinary field. So structural health monitoring in today's world, the interdisciplinary field, and without the contribution of civil engineers, without the contribution of mechanical engineers, without the contribution of electrical engineers, without the contribution of electronics engineers, without the contribution of computer science engineers, without the contribution of
Participants, please be patient. We have some technical problem. The session will resume soon.
I think it. I'm back. Okay. Okay. Sorry, participants. There are some network issues and got a power failure, and we'll just restart the things again. Yes. So I'll share my screen again, and let me. This is where it's here, right? Yeah. Yeah. So I think we are stopped. We have stopped here. Uh, you can see. So what I was trying to tell that AI-driven analytics is important, but before AI-driven analytics, you require a lot of things, and this architecture tells you where it is important and how is it important and how the civil engineering perspective is important in case of any kind of structural health monitoring technique. Okay. Now, just the last part of the presentation, and then we'll go to a small demonstration. I hope that you will enjoy that demonstration part. So just try to understand that I have told you that signal is coming from the acoustic emission. Now, what is the signal processing approach? So you see, signal processing approach is nothing but this. This is first thing you see, every defect and damage will generate some kind of AE signal or AE event. You have understood it. Next is, as the crack is created or the defect is created, AE wave will be propagating and will be sensed by AE sensor. That also you have seen. And this will pass through the pre-amplifier. Finally, it will be passing through a data acquisition system, and then the time versus amplitude wave. So you have seen that acoustic emission signal where time versus amplitude thing I have shown you. The time versus amplitude wave like data will be finally captured through software, and the signal thus you will be capturing can be processed through different signal processing tools, mathematical tools basically. They are nothing but You have learnt about Fourier transform in your third semester course, I think, Fourier transform. Okay, so this Fourier transform can be used to extract from that signal that will give you, that will help you to identify which kind of crack it is happening, where the crack is happening. So basically, if you see, if you can use different kind of mathematical tools like fast Fourier transform, short time Fourier transform, wavelet transform, then you can extract the nature of the crack, location of the crack, the extent of the crack, everything you should be able to find out from that. So this process signal thus can be used in combination with another one concept I will be showing you, that is called group velocity. Group velocity. So group velocity is what? That group velocity is basically, it is depends on material property and the physical system parameter like thickness, dimension, etc. So like every material, if you see every material through which if you pass any wave, that material will have a p wave velocity and s wave velocity. That is, longitudinal wave can propagate through the material, shear wave can be propagating through the material. So longitudinal wave and shear wave. So using the longitudinal wave velocity and shear wave velocity of the material, you can use the modulus of elasticity of the material and density of the material to find out the group velocity of the material. Okay, and that group velocity concept I'll just explain. So like how it is related, like if you know the group velocity, then what happens, like it's a very simple fundamental. Velocity multiplied by time, gives you what? Gives you distance. So when you get a velocity, and if you can identify the time, at what time that velocity is happening, and if you can get it extracted from the signal you have captured using your acoustic emission sensor, you will get the data of the distance where that defect has happened, right? So this is what is a typical diagram for group velocity, which is being taken from Wikipedia only. You can see from Wikipedia the definitions and all. So you see, this is what is actually a wave when it travels through any material. This is what happens. You see, what happens, you can see the picks and throws are proceeding, but you can see there is a backward movement. One is proceeding. You see, there is a proceeding of things like this. So these picks and throws, they are proceeding forward. Whereas you can see, it looks like there is a backward movement. So this backward movement is actually your phase, and this forward movement is your group. Okay. So basically, this shows a wave with group velocity and phase velocity going in different directions. The group velocity is positive, that is the envelope. Group velocity means if I do an envelope over it, I'll show you in the next diagram. If I do an envelope over it, so this is what is actually your group velocity. You can see this is what is your group velocity. So if I envelope it, I'll get a group velocity of it. And if that group velocity is positive, that is the envelope of wave moves rightward, while the phase velocity you can see that is moving in a reverse direction, that is actually negative. So that is the picks and throws move leftward. So one is moving rightward, one is moving leftward. So this is what is, sorry. Not visible. So this is what is actually, this is actually your group velocity and phase velocity concept. I'll not get into much detail. So you can see huh? Not visible. Shared now. Sharing stopped again. Now Now it is visible? Visible? Okay. So you can see that if you go to this YouTube video, you can see also for this group velocity and phase velocity. It's a very just a minute, just online online. Okay, so I think from this YouTube video you can check the participant who are present in the room who are physically watching. There is some issue with this projector. So you can also visit this and you can check it how group velocity and phase velocity is happening. It's a very interesting concept. So okay, it has come. So I'll just show you. So see, this is the video. Can you see how it is happening? No? So window is being shared. So that is why it is not coming. I think. I have to share another one. Anyway, I'm not getting into it. Time is not there. So let's move to next part. So again, I think I'll have to share. Okay, now please please see one demonstration. The simple demonstration. I'll just like to show you. I've shared my entire screen and just so typically you see. Can you see this? So I will try to demonstrate this signal processing thing using basically a tool called AGU Valen wavelet. Okay, AGU Valen wavelet. And this is a wavelet transformation tool. Now, before I get into this wavelet transformation, I explain you from a signal, if you want to extract the frequencies. So see the signal of acoustic emission, whatever you have received, that gives you time versus amplitude. So in that signal, lot of frequencies are hidden. So in case of a Fourier transform or a first Fourier transform, if you apply that mathematical first Fourier transform to it, then what you will get, you will actually get the frequency content, different frequency content along with its amplitudes. I'll show you with the diagram. However, if you want to find out at what time those frequencies are occurring, then you cannot get it through first Fourier transform. This is where the concept of short time Fourier transform or wavelet transform comes into picture, where you can get from a signal at what time which frequency is appearing. Okay, so considering this, you see this AGU Valen wavelet, this is a tool. You can directly download it from the internet. It is a free tool, and you can go to this tool. Here the link is given. and from the link you can download it. And after downloading it, I'll just show you now the demonstration part. So you please see the demonstration, and if you have any question during the demonstration, please ask me. Okay. So let's say, like when I was talking about the acoustic emission sensor and then collection of data. So, like when this data is collected, you get, can you see the Excel spreadsheet? Okay. So you see this collected data will be, once the acoustic emission signal is passing through the preamplifier, then data acquisition system, and it will be captured through your computer. Then in the computer, you will get for each of the AE event such kind of data in a CSV file or in case of a Excel spreadsheet. Okay. And you see in that you can get the source file name, then when it is being collected, what is the interval of the time, at what interval of time you are collecting the data, then signal units, all these things. And finally, you see the time of test will be given. And these are the data you need to have for, these are the data which is actually the amplitude values. And these are with the time. So let's say you are collecting the data with 0.01 microsecond or 0.001 microsecond. So every 0.001 microsecond value, you will be getting the value of each of the amplitude. Now, when you use this Valen wavelet concept, then you see you cannot just directly use the data, raw data, as being collected through the acoustic emission system. You need to little bit modify the data. So how will you modify it? You see the modification will be like this. The modification will look like this. So if I show you a data, so in the Valen system, through the software, if you want to put the data, you need to put it in a text file, something like this. So same data I have taken, and you see the at the first row you will have to give what? The time interval and how many number of steps of time you have calculated, that you take, and then all the amplitudes as you have got it from the AE system, that you copy and paste in a text document. So that will give you the signal. Now how this signal will look like? So for the valence system, if you go, you see this is what is your valence system. And here, after you download, you will get an icon. After you download and install the Valence software, you will get an icon like this. So if you click on this icon, it will open like this. Okay. So out of this, only one thing is actually free, that is this TR part. So you can use all these tools for free. So 1, 2, 3, 4. 4 tools you are having that you can use for free. You can play with any kind of high frequency data using this Valen tool. And this Valen tool gives the data transfer using wavelet transform, as well as there is another one transform that is called Chio-William transform. So wavelet transform, it uses a typical kind of wavelet called Gabor wavelet. So there are different types of mathematical functions for the wavelet. So one of the mathematical function for wavelet is Gabor wavelet. So Valen uses actually Gabor wavelet concept. Now the first step, what you'll have to do, you will have to import the data, whatever you had from the acoustic emission system, through this wave importer. So what I am doing, I am running this wave importer. Can you see the wave importer? So in this wave importer, what you do, you browse and you browse to, let's say I am going to my demo folder,
And in this demo folder, I am just trying to collect information for a concrete slab. I think I have forgotten to show you. I'll just show you. So just see it first. So I am taking a basically typical acoustic emission data collected. So what I am doing, I am just collecting this file. And you see, this this is basically coming, all the data is coming over here. And you can see, you can change your measurement range. So here you can change your measurement range from millivolt, because your data is coming, amplitude is coming in millivolts, right? So there is an option for changing your millivolts and all. I am keeping it here. And you can see the threshold I have mentioned for the acoustic emission, any signal, there is a threshold. And in that threshold, I have mentioned here 0.05 is the threshold. And at the end, you make a file from your text file, a TRA file. This TRA file is the input to the valence system. So you just create a TRA file. Now this is what is your signal. You can see this is what is your signal. So this is what the waveform has been collected through the acoustic emission sensor for any kind of one defect happened in some system. Okay. So now if the signal, then you can see this has been generated over here. So you can see this valent transient data. So after, from the sensor data, you will have to first create the valent transient data. Once you have created this valent transient data, then you see this is very interesting and it's very easy also. Okay. So you go to wavelet. Okay. So you go to wavelet. So you see, I go to wavelet and I choose this file and I open it. So where I have kept it, I have kept it in my demo folder, right? And you can see, you can go to your demo. I am going to my demo folder. So in this FDP folder, I have a demo folder. So I'm going to the demo, and you can see the sensor to PLB distance 100 millimeter. So this is the TRA file I have created. So I am just opening this file over here. So the file has been imported in the valence system. Okay. So the signal has been imported to the valence system. All are with me? Now you see, once you import it, you see there is a very interesting part over here. You can see that in this case, if I apply the transformation of this data, the wavelet transformation, okay? So you can see there is a icon over here that is called run transform, okay? So this run transform, if you do, it will automatically transform the data. And you see, from a single line graph with zigzag, you have got a two-dimensional graph with different kinds of colors. Have you observed it? Okay. So this is what is the beauty of the wavelet transform. So it has transformed your data. And you see, you can see this right-hand scaling factor. Here, the wavelet coefficients are being mentioned. And you can see this data, as I have mentioned you earlier, the initial data was time versus amplitude, right? Now you see this data, it has got a 3-dimension over here. What are those 3 dimensions? You can see this frequency is plotted in this range. On the other hand, time is plotted in this range. And you have different colors. Can you observe different colors? And these colors are identifying the energy of the signal, energy stored inside the signal. So these are called the wavelet energy. Okay. And wherever is the energy maximum, you can expect that your crack or your defect has happened in that region. So can anyone tell me, if red is the my maximum thing, where the crack is expected to occur? So you see the red zone is having, sorry, I have to do again the transfer. So red zone, you can see this red zone. So red zone is having the maximum energy. So you can expect your crack has happened in this zone. And if you see, if you just put your mouse over here and double click, you see, you get the details of at which frequency that has happened. You see this 45 kilohertz. You can see that 45 kilohertz at 94.10 microsecond, the wavelet coefficient value you can see, and at that time you may expect your wavelet value is maximum, and you need not to worry about it. Your Valen gives you an export of this data. You can go to this file and you can export the data to MS Excel. And if you export it, you get a data like this. You see all the Valen wavelet values with separated by all the frequencies, 1 kilohertz, 2 kilohertz, and here on in this side the time, in this side the frequency values, all the wavelet values you can get, and you can play with this data using any kind of tool of AI or machine learning, whatever. So if you are having multiple such kind of data, then comes your AI into picture, right? So this is how you need to process your data. Okay. So once you have done the wavelet transform, you see, I'll show you another one thing over here. Once you do the wavelet transform, you can see it in this three-dimensional representation also. And you see the three-dimensional representation, how beautifully it is coming, right? The three-dimensional representation give you the idea about how a data, simply a data in a time and amplitude level can be transformed into time frequency amplitude data. Okay, so this is what is your time frequency data. Can you observe this time frequency data? So in one axis you see there is a time, one axis you can see the frequency, one axis you can see the wavelet coefficient. So you can see the data in the time frequency zone. Okay, so once you have done with this, you see, once you have done with this, what you can do now, the job is to find out where this is happening. So I'll do one thing. I'll just close this and again I'll show you that. So before I go and find out where the defect is happening, I just want to show you another one slide. Just bear with me. So you please see this slide. So you see, this is a typical setup which we have done in a concrete slab. The concrete slab is 40 millimeter thick, and you see the crack is being simulated by a lead breaking. Okay, a pencil lead, if you break on the surface of any material kind of thing, then you can expect that there is a internal crack is getting developed. Okay, because it is a simulating kind of tool. So if the lead break is happening, and then there is a sensor, it is being transferred to preamplifier, and then this is being collected, and you can get this signal like this. So that signal we are processing. Now you see, now it is a known distance, 100 millimeter distance, you have broken the lead. So you are expected that your signal, whatever you will be getting, that will be able to identify that your crack is happening at a distance of 100 millimeter. So now I have explained you the group velocity and phase velocity concept. So this Valen tool itself gives you the facility to generate the group velocity curves for any kind of material. So how do you generate the group velocity curves? So you can go to this, you can again go to this you can again go to this Valen control panel, and then you can find out a icon over here, that is the dispersion curve. Okay, so sorry, I have generated this again, let it be here. You go to this dispersion. So if you do this dispersion, then in this dispersion I have already generated it. I'll show you that one only because it takes some time to generate. But you can see in this edit, there is a part called calculate curves. Can you see this calculate curves? So what curves it will generate? it will generate, it will create, or it will calculate the curves for group velocity and phase velocity for a material of particular thickness. So what will be the input to this? So if I do the calculate curves, you see here it is written aluminum. So if I want to do it for concrete, if I want to do it for anything else, I can calculate it. So I just give it the material name, and then I give the P wave velocity through the material, that is longitudinal wave velocity. I give the S wave velocity, that is the CR wave velocity, and then I give the thickness of the material or the plate. And then if I do the start, then it will generate the symmetric and anti-symmetric group velocity curves as well as phase velocity curves for that material. And you please understand, this group velocity and phase velocity curve for a particular material, for a particular thickness, will remain same. This is all about the material property. It will depend upon the material thickness, it will depend upon the modulus of elasticity, it will depend upon its P wave velocity, S wave velocity. Okay. So already I have imported the curve, some curve I have generated for concrete. So I'll show you. So this is what is the curve for concrete. So let me show you through my demo thing. So I have already generated. So dispersion curve for concrete BDC. So I'm just opening it. So you see, these many things are hidden over here. So if I do go to edit and I do show and hide curves. So if I do all the curves, you can see A0, A1, A2, these are the anti-symmetric curves. So these are curves which are basically basically the, as you know, that longitudinal wave velocity and CR wave velocity, their propagation is different. So it's similar concept happens in case of this group velocity and phase velocity also. So you get anti-symmetric curves and symmetric curves. So all kinds of curves you can get over here. So if you see this curve, typically what you are getting, just for your conceptual understanding, what you are typically getting from this curve, actually you are getting on this side, you see, you are getting the frequencies, and the frequencies are in megahertz. You can see there is a frequency, and this frequency is in megahertz. And on this side, you are getting the group velocity values. Okay. So what we have observed, it's not possible to explain everything. What we have observed in our experimental thing, that in case of concrete, it's a kind of research. So in case of concrete, we have found out that symmetric and anti-symmetric mode both in the first and second, that is A1 and S1, these symmetric and anti-symmetric curves are more getting relevant in case of finding out defects in case of concrete. Whereas in case of aluminium or in case of steel, if you go, you can find it out using A0 or S0 thing also. Okay. So what you need to do, you know, like very simple concept, like you have wavelet. So this is the diagram I have imported, and I have shown you the transform of this sample signal. Okay. So you have seen it. Now you see, if I now, there is an option, you see in this edit, you can see there is an option, no, on import. There is an edit. In the edit option, you can see there is an option of importing the dispersion curve. So what we are doing, we are testing, we are doing it in the concrete, and in on that concrete, from that concrete with the pencil lead break, that means with the crack, we have found out some signal. Now on that signal, I will be superimposing the group velocity curve, and I am not going to do anything. The software will do it for me. So how it will be superimposed? I will import the dispersion curve. And what dispersion curve? I'll import this dispersion curve. So if I import this dispersion curve, it will show me the P wave velocity and S wave velocity with what I have created this group velocity curve. And I have, you see this distance to source, it is by default, it is showing 10. But what I have said, that crack, we are expected to have it at 100 millimeter, right? So I'll show you. So now you see, if I import it, so you see these are the two curves imported. So these are the group velocity curve I have shown you earlier in that group velocity thing. Okay. So once you have imported these two curves, so now you see these two imported curve, one is A1 that is being shown with green, and another one is S1 that is being shown with red. Okay. Once they are imported, what distance you have seen over there? 10, right? Now you see there is an option over here, distance to source. I don't know what is the distance, right? So I can do a trial and error. So let me make it 50. So let me make it 50. So you see, this is what is happening, right? So one card is moving through this. So if I go on keeping this way, so if I go on trying it way, then you see, in case if I am moving it to 100 millimeter, let's say, if I put it 100 millimeter, then you see both the S1 and A1, both the curves are being passing either through the central region of the high energy zone, or the high energy zone is just above the zone of another one card. So if I consider this card, then you see, if I click on this, then you can see the frequency. So 43 kilohertz is the frequency, 93.50, right? So if you get this 43 kilohertz and 93.50, so what you are getting? You are getting at what frequency your group velocity curve is crossing, right? Your group velocity curve is crossing at 43 kilohertz frequency at a particular time of 93.50 microsecond, correct? Now in the group velocity curve, as I have shown you, in the group velocity curve, you had a relation between frequency and what? Group velocity. So from that, if you can find out, so if I go back to the group velocity curve, I think I have closed it. So if I go to the group velocity curve, that means the dispersion curve, and if I open it, dispersion curve, if I open it, you can see this is the group velocity curve. So I am playing with this red one, that is the symmetric one. So in this symmetric curve, you see this is what is 0.04 megahertz. That means this is actually 40 megahertz, right? So this is 40 kilohertz, and this is 50 kilohertz. So in between this, there will be a 43 kilohertz range. So I can export it, or I can find out from this graph the velocity of travel. So it will come around 1 or 1.5, 1.1. So that also you can find out by exporting the data from this. So once you know, so if you see, I'll show you with this export to MS Excel, that will clear you more. So if I export to MS Excel, this is the group velocity data, right? So group velocity data, you see what group velocity we are using? We are using S1, right? So in S1 group velocity, you see what frequency we have got? 0.43. So I am going to 0.43. So where is 0.43? So 0.42, 0.042, you see here 0.423, something like this, 6 decimal, 10 decimal places. So if I interpolate and can find out, you will get this velocity is happening around the velocity at 43 kilohertz is coming around 1.1. Okay, and if you multiply it with the time, that is the microsecond, whatever you are getting from the wavelet transform data, that is 93.50 multiplied by 1.1 or 1.15, if you do, you will get approximately 100 millimeter. So that will help you to understand where the crack has happened. So this is actually a localization problem. So I hope I have explained. It's not possible to explain everything about this valence. So you can do hands-on on this. Any high frequency signal, if you want to do time frequency domain analysis, you can use it. And it's a very helpful tool for doing it. Those who do not want to do coding for transformation analysis. Okay. So I think I am done with it. And if you have any questions, then you can ask, or you can send it to my email ID. So now the forum is open for question.
Participants are asked to carry their questions. We are very much thankful to Dr. Sanjay Sengupta for this wonderful and very informative session about structural health monitoring that is used for smart city health monitoring. So I would ask the participants to ask their question in the chat box they can post.
Oh, no questions, I think. From the sitting audience, if you have any questions. Fine, I think then.
Sir, I have a question. I think I can
Yes.
ask from behalf of the
Yeah.
participants. So, I would like to ask that uh, how since the sensors are very costly, so how we can make it more practical by introducing latest technology for reducing the cost that we are for the health monitoring using sensor based analysis using acoustic emission or any other sensor type based health monitoring system.
A very relevant question, very relevant question. And one thing I think this is where actually the innovations and things should come, as well as in our Indian scenario. We are now, I think, too much focusing on data analytics and other things, but rather than physically developing a system for ourselves, right? So these systems, if you go to American market, it comes for 28 lakhs rupees. But if we can develop similar kind of system in our Indian perspective, that will be really good. Because you see, is sensor is a piezoelectric sensor that is difficult to develop. In our like institute, should be very difficult to develop. But I think it is possible to be taken up by IITs and NITs. They should be focusing on the sensor development thing. We are not much focusing on the sensor development. We are all buying from the outside world. Okay. And what we are doing, we are gathering data and we are just analyzing the data. Okay. Using various tools. But considering this thought process, I think from our research group in our institute, we have submitted research proposal to SCRB, Structural Engineering Research Board, okay, for giving us some fund for getting this kind of indigenous system developed. But somehow that proposal was considered, and it was said that it was technically beneficial, but due to fund unavailability, they did not give us. But in recent time, what we have done, using some of our institutional fund, we are now trying to develop a system where we should be able to develop a pre-amplifier and data acquisition system, and this computer monitoring system. Okay, so for that we are trying to do the procuring. Okay, all the things can be done within a cost of 50,000. 50,000 rupees. Okay, along with the sensor, along with the sensor. But you know, the challenge is all the other materials for preamplifier, data acquisition system, all the things are available in Indian market. But once you go for sensor, you either need to depend on China or America. So that is where our project is now stuck, internal development. But we are hoping that we will be able to break this barrier, and we should be able to develop a kind of system in our own laboratory where the preamplifier thing we can itself design ourselves and the data acquisition system. It is not very difficult. Electronically, if you see, it is not very difficult. That is what we are collaborating with the electronics department also. Same attempt has been made with NIT Durgapur and CSIR, CMERI. They have also developed, but they could not market it properly. They have also developed some system, but they could not market it properly. There is another one problem of incubation also. Okay. So unless and until government focuses on such kind of things for development, I think this is very difficult to have it at a low cost in our Indian scenario or Indian perspective. So hope government will be focusing on this kind of things and it will be developed. Because till now, whatever research is happening in this area in India and whatever practical implementations they are also trying, that is happening through outside sensors, outside preamplifiers and other things. You know, there is a huge application of acoustic emission in case of aerospace industry. Okay, every aircraft is tested with this acoustic emission device. Every aircraft, before it is being commissioned, that is being tested with this one. Okay, so in the air tunnel also that is being tested with acoustic emission sensors. That how the things can be tracked in case of this one. But all the things are being now procured from the outside. Okay, so even though like in China. In China, I think Jiangsu University, I think there is one university. They have developed their own, and they have a small kind of rod, and in that sensor is attached, and if you just put it on that, that will sense it and give you acoustic emission signal. So in the university lab, they have developed. So such kind of development is required to make it low cost and to make it implementable for the structural health monitoring in the real-time perspective in case of our country.
Thank you, sir.
Thank you. Thank you.
So that comes with our conclusion, and I would ask our HOD sir to give concluding remarks and the final closure of this FDP. I hope the participants have enjoyed the sessions thoroughly, and I would also ask the participants to give their feedback for the concluding remarks.
Okay, so I was only the speaker, so now come back to my administrative part. So this is the requirement of giving a validatory thanks for this faculty development program. So on behalf of Dr. BCREC Engineering College, Department of Civil Engineering, I'd like to thank all the participants present for this FDP and patiently listening, asking questions, making it interactive with all the speakers and make it fruitful and effective for a better learning in the perspective of smart cities. So from the core of my heart, I thank all the participants, because without your participation, this would not have been successful. Next, I'd like to thank all the speakers who have given their valuable time to be present in online, or either in online or offline mode, and present it their thought processes regarding the smart cities, the smart structures, and other things. So I thank every one of them. I'd like to thank the students who have joined this FDP come workshop program where students have also interacted, and I'd like to thank the coordinator of this FDP, Professor Shobhan Roy and Professor Anupam Viswas, for making it, for arranging it, taking lots of pains for arranging speakers, different kinds of approvals and other things, and then finally making it a successful one with lots of outside participation also. I'd like to thank all the faculty members of our department who have actively participated in this faculty development program. I'd like to thank the management of this institute, principal sir, uh, and chief advisor sir, for giving us the opportunity for conducting this kind of FDP. I'd like to thank our support and conservancy staffs who have made it possible to happen in a clean environment with all kinds of logistics in place. So with this, I hope that there is a good learning opportunity for all of us through this FDP. And in the near future, we are hoping to conduct many more such kind of programs in our department. Will be expecting that as the outside participants you have participated, you will be also participating in our upcoming events also. So thank you very much for your participation and happy learning in this FDP. Thank you.
Thank you, sir. So it has been a all-round experience for all the participants. I hope you have enjoyed and have a great session throughout these 6 days. Uh, I would like the participants to share their thought. If they can post. Along with this, I would ask the participant to give a short quiz which will be shared in your WhatsApp group. So try to submit the quiz within today by today evening. Uh, with this concluding remarks, I am closing the session and I wish best wishes for all the participants. Hope we will see again. Thank you.